You wake up, you breathe, your coffee heats, your phone charges, stars burn, galaxies spin. Every single motion in this universe depends on rules so simple they fit on a napkin, yet so absolute they decide whether reality itself survives. We call it thermodynamics, but these aren't gentle suggestions. They're iron laws that stand between you and the death of everything. Heat flows, energy spreads, entropy climbs. And somewhere in those three facts lies the thin thread keeping the cosmos from collapsing into frozen silence or dissolving into uniform gray nothing. What are these rules? Why do they work? And what happens the moment they stop working? Energy shifts forms, but the total never changes. You can't create it from nothing, and you can't delete it. Second law, entropy always increases in a closed system. Disorder climbs, heat spreads from hot to cold, never the reverse. Coffee cools to room temperature, not hotter. This one-way street defines time itself. Third law, you can't reach absolute zero Kelvin, the temperature where all atomic motion stops. You can get close. Researchers reached a billionth of a degree above zero in laboratories, but touching 0 Kelvin? Impossible. These three laws appeared over 100 years of work starting in the 1820s when Sadi Carnot studied steam engines in France. Nicolas Léonard Sadi Carnot lived 36 years and died in 1832, but his 1824 book, Reflections on the Motive Power of Fire, changed everything. He asked, how efficient can a heat engine be? The answer became the Carnot efficiency formula. Maximum efficiency equals the temperature difference between hot source and cold sink divided by the hot source temperature in Kelvin. If you run a power plant with steam at 600 Kelvin and cool it with air at 300 Kelvin, your maximum possible efficiency is 50%. Real engines get 30 to 40%. Your car engine? 20% or less compared to its Carnot limit of 37%. Friction and turbulence steal the rest. The second law emerged from Rudolf Clausius in 1850 and William Thomson, later Lord Kelvin, in 1851. They realized heat engines must waste heat. Perfect efficiency violates the second law. Ludwig Boltzmann connected entropy to probability in 1877 with his equation S equals K times the natural log of W, where S is entropy, W is the number of possible microstates, and K is the Boltzmann constant. That constant, 1.380649 times 10 to the negative 23 joules per Kelvin, bridges temperature and energy at the particle level. It's engraved on Boltzmann's tombstone in Vienna. Max Planck gave it the name and measured it at 1.346 times 10 to the negative 23 joules per Kelvin in 1900, about 2.5% lower than today's value. In November 2018, the Kelvin was redefined with the Boltzmann constant fixed at its exact current value. Acoustic gas thermometry at the National Institute of Standards and Technology achieved uncertainties below 1 part per million. Also, comment from which city you're hearing this from. This script is researched and factual, using sources including Nature Physics, published February 4th, 2025, showing false vacuum decay experiments on quantum annulars with 5,564 qubits, and Physical Review D, published February 27th, 2025, examining how fast protons could decay in different regions of space and time by Human de Vudiazel and Peter Denton at Brookhaven National Laboratory. Now back to the information. The universe becomes a dilute soup of photons and leptons at near uniform temperature. This end state has a name: heat death. Jean-Sylvain Bailly, a French astronomer, first suggested in 1777 that all bodies in the universe cool off until they become too cold to support life, mentioned in his correspondence with Voltaire. Lord Kelvin formalized it in 1852. He called it the heat-death paradox. If the universe were infinitely old, it should already be at maximum entropy. But stars still burn, temperature differences exist, work still happens, therefore the universe can't be infinitely old. The paradox helped establish that the universe had a beginning. The Big Bang model confirmed it. The universe is 13.8 billion years old. It started in a low entropy state, highly ordered, and has been sliding toward disorder ever since. Gravity played a key role. The early universe had matter distributed almost uniformly. Small density fluctuations grew under gravity into stars, galaxies, and galaxy clusters. This seems to contradict the second law because stars and galaxies look more ordered than a uniform gas. But gravitational collapse releases enormous energy as heat and radiation, increasing total entropy far more than the local decrease from structure formation. The second law wins. Every star that forms increases net entropy. Every supernova explosion increases entropy. Every black hole that swallows matter increases entropy. Black holes are entropy engines. A black hole with one galaxy mass, about 100 billion solar masses, has a Hawking radiation decay time on the order of 10 to the 100th power years, according to calculations updated in Wikipedia as of 16 hours ago based on Stephen Hawking's 1974 work. Some supermassive black holes could grow to 10 to the 14th power solar masses during supercluster collapse. Those would evaporate over 10 to the 106th power years. After that, the universe enters the dark era. Only diffuse photons and leptons remain. They argue the universe might grow more complex over time. Entropy measures energy dispersion, not just visual mess. Most entropy sits in radiation fields, especially the cosmic microwave background at 2.7 Kelvin today. Entropy density varies. Cold molecular clouds have low density. The CMB has high density. If the cosmological constant is zero, the universe cools toward absolute zero over immense timescales. If the cosmological constant is positive, as current dark energy measurements suggest, the universe approaches a non-zero temperature and maximum entropy, where no further work is possible. Thermodynamic equilibrium, the heat death. Current data from the Wilkinson microwave anisotropy probe and the Planck satellite favor a flat universe with a positive cosmological constant. That points toward heat death, not a big crunch. The timeline stretches beyond imagination. Stellar era ends in 10 to the 14th power years when the last red dwarfs fade. Degenerate era begins. White dwarfs and neutron stars cool. Protons might decay. The proton lifetime lower limit sits at 10 to the 34th power years based on experiments at Super Kamiokande in Japan. Published results setting. Limits at 6.6 times 10 to the 34th years for decay to an antimuon and neutral pion, and 1.67 times 10 to the 34th years for decay to a positron and neutral pion. Grand unified theories predicted shorter lifetimes. Early gut models from the 1970s suggested 10 to the 31st power years. Those were ruled out. Modern supersymmetric guts push the proton lifetime to 10 to the 34th or 36th power years. Non-SUSY gut maximum sits at 1.4 times 10 to the 36th power years. The absolute theoretical upper bound reaches 6 times 10 to the 39th power years for supersymmetric models. If protons decay, even atomic nuclei disintegrate. Matter itself becomes unstable. Human Davudiasol and Peter Denton at Brookhaven National Laboratory asked a new question in Physical Review, D Volume 111, published February 27, 2025. Could the proton lifetime vary across space and time? Earth-based experiments constrain the present lifetime here. But what about the distant past or other regions of the Milky Way? They calculated that if protons decayed producing heat, the Earth's solid iron core would melt if the proton lifetime fell below 2 times 10 to the 18th power years. The core has been solid for 1 to 1.5 billion years, possibly as long as 4.2 billion years according to different geological estimates. It's not molten, so the local proton lifetime exceeds their threshold. That's still 8 orders of magnitude less than the universe's current age. They propose a new long-range force could vary proton stability as the Sun orbits the galactic center every 230 million years. The idea remains speculative, but opens questions about whether fundamental constants truly stay constant everywhere and everywhen. They evaporate via Hawking radiation. A solar mass black hole evaporates in 10 to the 67th power years. A supermassive black hole with 1 billion solar masses takes 10 to the 98th power years. The largest black holes, 10 to the 14th power solar masses, need 10 to the 106th power years. As black holes evaporate, they radiate particles and increase entropy. The radiation carries away mass energy until nothing remains but photons. Dark era follows. By 10 to the 106th power years, even the largest black holes have evaporated. The universe contains only a dilute gas of photons, neutrinos, electrons, and positrons. Temperature approaches uniformity. Entropy reaches near maximum. No energy gradients exist. No work can be performed. Heat death. But this assumes the proton doesn't decay and the vacuum remains stable. If protons decay in the degenerate era, matter vanishes sooner. If the vacuum decays, everything changes immediately. The Higgs field sets particle masses. Discovery at CERN in 2012. Higgs mass 125 giga-electron volts. Top quark 173 giga-electron volts. These values place the vacuum in metastable territory. Not stable, not imminently unstable. A lower energy state exists. If the Higgs tunnels there, particle masses unravel, atoms disintegrate. The transition spreads at light speed. A bubble of destruction expands. Sidney Coleman and Frank DeLucia calculated rates in 1980. The Standard Model vacuum lifetime was estimated at 10 to the 139 power years in 2018. July 2024, Slovenia's Josef Stefan Institute revised it. 10 to the 790th power years. Still vastly longer than cosmic age. No occasion for anxiety, they concluded. In January 2024, An Italian-English collaboration published results in Nature Physics, observing false vacuum decay in ultra-cold sodium gas. Newcastle University professor Ian Moss and Dr. Tom Billam showed that bubbles emerge as thermal fluctuations activate vacuum decay. The experiment cooled sodium atoms to less than a microkelvin above absolute zero. The atom's spins aligned with an external magnetic field, creating a metastable state. Increasing the field strength triggered a phase transition. Bubbles of the new phase formed and spread. The quantum field origin of the decay was confirmed. This marked the first experimental observation of bubble nucleation driving false vacuum decay. The process mirrors theoretical predictions about the early universe. Some inflationary models propose that the Big Bang resulted from false vacuum decay releasing enormous energy. Researchers at the Chinese Academy of Sciences Wuhan Institute of Physics and Mathematics presented in 2014 mathematical demonstrations that the universe could have spontaneously created from nothing through quantum fluctuations of a metastable false vacuum, causing an expanding bubble of true vacuum. Cosmic inflation might be an effect of the Higgs field trapped in a false vacuum state, then decaying. Alan Guth's original 1981 inflation proposal involved quantum tunneling. Andre Linde, Andreas Albrecht, and Paul Steinhardt later developed slow-roll inflation without tunneling to preserve a homogeneous and isotropic universe. Vacuum decay remains a low-probability event on human or even cosmic timescales. But quantum mechanics says if something can happen, it eventually will. The longer the universe exists, the more chances arise for a fatal quantum fluctuation. Black holes might catalyze vacuum decay. Papers from 2017 onward examined false vacuum decay around black holes. If a bubble nucleates near a black hole's event horizon, the black hole's gravitational effects alter the decay rate. Thermal fluctuations at the black hole's Hawking temperature can activate bubbles with finite energy. The bubble then tunnels to a lower energy state. Whether this accelerates or inhibits decay depends on the black hole mass, the energy difference between false and true vacuum, and the bubble's initial configuration. Current calculations suggest black holes don't significantly threaten our vacuum within observable timeframes. Between heat death and vacuum decay, the universe faces other existential scenarios. If the cosmological constant changes or dark energy evolves, the universe's expansion could accelerate without bound, leading to a big rip. In this scenario, space expands faster than light can traverse it. Galaxy clusters unbind, galaxies dissolve, star systems tear apart, eventually even atoms shred. The Big Rip timeline depends on the equation of state for dark energy. Current observations favor cosmological constant, which doesn't produce a Big Rip, but uncertainty remains. If dark energy is phantom energy with an equation of state parameter less than -1, a Big Rip could occur in finite time, possibly 20 billion years or less, depending on parameters. Another possibility, the universe undergoes cyclic phases. Roger Penrose's conformal cyclic cosmology proposes that after the heat death, when only massless particles remain, the universe loses any sense of scale. Time becomes meaningless. The end of one aeon matches the beginning of the next. The Big Bang repeats. Each cycle increases total entropy, but structure can reemerge. This remains speculative. Most physicists favor a single-phase universe heading toward heat death. The three laws of thermodynamics make heat death or something equivalent nearly inevitable unless new physics intervenes. The universe's uniformity in time directly produces energy conservation. The second law, entropy increase, stems from statistics. Boltzmann showed that entropy measures the number of microscopic arrangements corresponding to a macroscopic state. A glass of water has far more ways to arrange its 10 to the 24th power molecules in a disordered mixed state than in an ordered state with cold molecules on one side and hot on the other. Systems evolve toward arrangements with more possibilities because those arrangements are overwhelmingly more probable. It's not that disorder is preferred, it's that disorder is more common. A deck of cards has one perfect order, ace through king in each suit. It has about 10 to the 67th power random shuffles. After shuffling, you're vastly more likely to see chaos than order, not because the universe wants chaos, but because chaos has more configurations. The third law, the impossibility of reaching absolute zero, connects to quantum mechanics. At low temperatures, quantum effects dominate. Cooling requires removing energy, but the Heisenberg Uncertainty Principle prevents simultaneously knowing a particle's position and momentum with arbitrary precision. As temperature drops, particles occupy lower energy quantum states. Reaching absolute zero would mean all particles sit in the ground state with zero kinetic energy. That would violate uncertainty. Position becomes defined, momentum must become uncertain. The particle gains kinetic energy. You can't pin it to zero. Experimentalists reached temperatures below a nanokelvin. MIT researchers achieved 500 picokelvin in 2003 using ultra-cold sodium atoms. In 2015, the Corey experiment cooled a ton of copper to 6 millikelvin, searching for neutrinoless double beta decay. but absolute zero remains forever out of reach. This script is researched and factual, using sources including Britannica's thermodynamics entry, updated December 5, 2025, discussing entropy's statistical interpretation and Boltzmann's constant, and MIT News explaining Carnot efficiency with quotes from Professor Robert Jaffe, who co-teaches a course on the physics of energy. Now back to the information. The three laws prevent the universe from freezing over or dissolving immediately because they establish stability zones. Energy can't vanish, it can only transform. That means the total energy in the universe remains constant even as it spreads and dilutes. Heat flows from hot to cold, creating temperature gradients that drive processes. Stars burn because their cores are hotter than their surfaces. The temperature difference powers fusion and radiation. When gradients vanish, processes stop, but that takes time. Entropy increases slowly in large systems. A cup of coffee cools in an hour. The sun will burn for 10 billion years total, 5 billion remain. The universe needs 10 to the 106th power years to approach maximum entropy, even under optimistic heat-death timelines. That delay comes from the sheer scale. The universe contains around 10 to the 80 power particles. Each particle contributes to the entropy calculation. Mixing them into a uniform state requires countless interactions. Photons scatter, atoms collide. Heat radiates, gravity pulls. Each interaction nudges the system closer to equilibrium. But with 10 to the 80 power particles, equilibrium is a long way off. The third law ensures that even as the universe cools, it never fully stops. Motion persists. Quantum fluctuations continue. Zero-point energy, the ground state energy of quantum fields, never disappears. Even in the vacuum of space, virtual particles pop in and out of existence. The Casimir effect demonstrates this. Place two uncharged metal plates close together in a vacuum. Quantum fluctuations in the electromagnetic field create a measurable attractive force between the plates. The vacuum isn't empty, it seethes with energy. That energy prevents total stillness. Absolute zero can't be reached, so absolute death can't occur in the quantum sense. Fluctuations remain. Whether those fluctuations allow new structures to form in the far future is unknown. Some speculate that random quantum fluctuations could birth new universes via quantum tunneling, even in a heat-dead cosmos. The probability is infinitesimal, but infinity is a long time. If heat death takes 10 to the 106th power years and the universe persists. For 10 to the 150th power years or longer, low probability quantum events become almost certain eventually. Boltzmann himself considered this. He proposed Boltzmann brains, the idea that random fluctuations in a heat-dead universe could spontaneously assemble conscious observers. A Boltzmann brain is a self-aware entity that arises by chance from thermal or quantum noise, fully formed with false memories of a past that never happened. If the universe reaches equilibrium and sits there for eternity, Boltzmann brains become more probable than brains that evolved through normal processes. This is called the Boltzmann brain paradox. Current cosmology with accelerating expansion may avoid it. The cosmological horizon limits the volume we can ever interact with. Regions beyond the horizon evolve independently. Boltzmann brains can't form in volumes we'll never access. That radiation increases entropy. All ordinary matter, atoms, molecules, stars, planets, ultimately dissolves into a gas of photons and leptons. The degenerate era ends early. Black hole era still follows. Black holes remain immune to proton decay because their interiors are hidden behind event horizons. But even black holes evaporate. Hawking radiation ensures that. Stephen Hawking discovered in 1974 that black holes emit thermal radiation due to quantum effects near the event horizon. Virtual particle pairs form at the horizon. One particle falls in, the other escapes. The escaping particle carries energy away. The black hole loses mass. Temperature rises as the black hole shrinks. A solar mass black hole has a Hawking temperature of about 60 nanokelvin. A black hole with the mass of the moon would be around 100 Kelvin. Micro black holes could be hot enough to glow visibly if they existed. As a black hole evaporates, its temperature increases and radiation accelerates. The final moments release a burst of high-energy particles. Then, nothing remains. The black hole's entropy has been transferred to the radiation, total entropy increased. Even black holes, the most extreme gravitational objects in the universe, obey the second law. They're entropy maximizers. A black hole's entropy is proportional to the area of its event horizon measured in Planck units. That's the Bekenstein-Hawking formula. S equals k times c cubed times a divided by 4 times g times h bar, where a is the area, g is Newton's gravitational constant, c is the speed of light, h bar is the reduced Planck constant, and k is Boltzmann's constant. This links gravity, quantum mechanics, and thermodynamics in a single equation. It suggests that information falling into a black hole is preserved in some form on the horizon, leading to debates about the black hole information paradox and holographic principles. Those discussions reach beyond the scope here. What matters? Black holes increase entropy. Their evaporation spreads energy across the universe. Heat death advances. Matter dissolves. The bubble's edge moves at light speed. No warning arrives. The transition is instantaneous from the perspective of anything in the bubble's path. One moment, physics works. The next, it doesn't. This is more abrupt than heat death. Heat death unfolds over eons. Vacuum decay is a guillotine. Fortunately, as mentioned, the standard model vacuum lifetime vastly exceeds the current cosmic age. The risk is not immediate. Some physicists argue that if our universe's vacuum were truly unstable, it would have decayed already. The universe is 13.8 billion years old. That's a long time for quantum fluctuations to explore possibilities. The fact that the vacuum persists suggests stability, but metastability is tricky. A metastable state can last far longer than its characteristic tunneling time if the energy barrier is large. The Higgs field's potential has a large barrier according to calculations. Tunneling probability is exponentially suppressed by the barrier height. Make the barrier twice as high, and the tunneling probability drops exponentially. The barrier's height depends on the precise masses of the Higgs boson and the top quark. Measurements at the Large Hadron Collider put the Higgs mass at 125.1 giga electron volts, and the top quark mass at 172.76 giga electron volts. These values place the electroweak vacuum in the metastable region, not fully stable, not imminently unstable. Future colliders with more precise measurements could tighten the constraints. An electron-positron collider could measure the top quark mass and Higgs self-coupling with higher accuracy, refining vacuum stability calculations. If the top quark were a bit lighter, or the Higgs a bit heavier, the vacuum might be stable. If the reverse, instability grows, we're apparently balanced on a knife edge. Why? Nobody knows. It's one of the fine-tuning puzzles in cosmology. The Higgs field's value determines not just vacuum stability, but also particle masses, which determine chemistry, which determines life. If the Higgs field were much different, atoms wouldn't form, stars wouldn't burn, life wouldn't arise. The fact that we exist to ask the question suggests we live in a universe where the Higgs field is just right. That's anthropic reasoning. Some find it unsatisfying, others see it as the only explanation available. Multiverse theories propose countless universes with different Higgs field values. We inhabit one where the value permits observers. The others exist, but remain unobservable because they're lifeless or structureless. These laws prevent arbitrary changes. You can't create charge from nothing. Charged particles pair produce. Electron and positron, total charge 0. They annihilate into photons carrying no charge. Charge, conserved always. Baryon. Number conservation keeps protons stable in the standard model. Protons have baryon number 1. No lighter baryon exists. Grand unified theories violate this, allowing proton decay. Searches continue at Super Kamiokande, upgraded to Hyper Kamiokande with 5 to 10 times better sensitivity. Einstein's field equations, published in 1915, link geometry to stress energy. The cosmological constant, lambda, appears in the equations as a term representing vacuum energy. Observations from the late 1990s, particularly type Ia supernova surveys, show the universe's expansion is accelerating. Dark energy, which behaves like a cosmological constant, drives the acceleration. About 68% of the universe's energy density is dark energy. 27% is dark matter. 5% is ordinary matter. Dark energy's nature remains unknown. It could be a true cosmological constant, energy intrinsic to space itself, unchanging over time. It could be a dynamic field, quintessence, which evolves. It could be a sign that general relativity breaks down on cosmic scales. Whatever it is, dark energy opposes gravitational collapse. It prevents the universe from contracting into a big crunch. It pushes galaxies apart. Over billions of years, galaxies beyond our local group will recede beyond the cosmic horizon. We'll never see them again. Stars in our local group remain gravitationally bound. The Milky Way and Andromeda will merge in about 4 billion years. But everything else vanishes. In trillions of years, an observer in our galaxy would see a universe containing only the Milky Way-Andromeda merger remnant surrounded by darkness. No distant galaxies. No cosmic microwave background, redshifted beyond detection. Just one galaxy in an expanding void. If dark energy continues, this is the future. If it fades, the universe could recollapse. If it strengthens, a big rip occurs. Current data favor a cosmological constant. That means eternal expansion and heat death eventually. Quantum mechanics says that observables are probabilistic. You can't predict exactly when a radioactive atom decays. You can only give probabilities. The same applies to vacuum decay, proton decay, and thermal fluctuations. The second law of thermodynamics is statistical, not deterministic. Over short times in small systems, entropy can decrease. If you watch 10 gas molecules in a box, sometimes they'll randomly cluster in one corner. Decreasing entropy momentarily, wait long enough, and they spread out again. For a glass of water with 10 to the 24th power molecules, the probability of all cold molecules spontaneously gathering on one side is so low that it won't happen in the age of the universe multiplied by a googol. But it's not impossible. Quantum mechanics says that if something is not forbidden by a conservation law, it will happen given enough time. Virtual black holes, particles tunneling through barriers, vacuum fluctuations, creating matter, all these occur with tiny probabilities. Across cosmic timescales and volumes, tiny probabilities add up. A universe that lasts forever will see everything that can happen. That's both reassuring and terrifying. Reassuring because it means the universe is rich with possibilities. Terrifying because it includes vacuum decay and Boltzmann brains. But forever is longer than heat death. If the universe reaches equilibrium in 10 to the 106th power years and that's the end, then forever stops. Eternity gets cut short. Thermodynamics wins. No more fluctuations matter because no more work can be done. Time becomes meaningless when nothing changes. First, energy conservation ensures that energy remains available even as it spreads. The total energy budget never depletes, it just dilutes. Stars fuse hydrogen into helium, releasing energy. That energy radiates into space, warming planets, driving weather, powering life. Eventually, the energy reaches the cosmic microwave background, adding to its temperature. The CMB temperature drops as the universe expands. Today, it's 2.7 Kelvin. In a trillion years, it'll be lower, but it won't hit zero. The third law forbids it. Second, entropy increase is gradual. Mixing takes time. A hot object placed in a cold room doesn't cool instantly. Heat conducts through air molecules. Photons radiate from the object's surface. Convection currents circulate air. Each process has a rate. For everyday objects, equilibrium arrives in minutes or hours. For stars, it takes billions of years. For the universe, far longer. The size of the system determines the timescale. The observable universe has a radius of about 46 billion light years. Information can't travel faster than light. Different regions of the universe are causally disconnected. They can't equilibrate. That slows entropy growth. Only regions within each other's light cones can interact and share entropy. The accelerating expansion driven by dark energy makes this worse. As the universe expands faster, the cosmic horizon shrinks. Fewer and fewer regions can communicate. Entropy increases within each horizon volume, but the volumes can't mix with each other. Whether total entropy increases or each isolated region reaches its own equilibrium is debatable. Third, quantum mechanics keeps the system dynamic. Zero-point energy and quantum fluctuations ensure particles never truly rest. Even at temperatures approaching 0 Kelvin, atoms jiggle due to quantum uncertainty. The Heisenberg Uncertainty Principle says position and momentum can't both be zero. If position is well defined, momentum is uncertain. If momentum is near zero, position is uncertain. This quantum jitter prevents particles from freezing into a static lattice. Superfluids and superconductors exhibit strange quantum behaviors at low temperatures, but they're not frozen in the classical sense. Atoms move in coordinated quantum states. Liquid helium becomes a superfluid below 2.17 Kelvin, flowing without viscosity. Superconductors conduct electricity without resistance below critical temperatures. These phases show that low temperature doesn't mean death. It means weird quantum life. Whether the universe's final state resembles a superfluid on a cosmic scale is speculative. Some models propose that the vacuum itself is a kind of superfluid. If so, the heat-dead universe might exhibit large-scale quantum coherence. Again, speculative, but the rules allow it. The energy-time uncertainty principle, delta E times delta T greater than or equal to h bar over 2, says that energy can fluctuate by delta E for a time delta T as long as the product respects Planck's constant. Borrow energy from the vacuum, create a particle, pay it back before the universe notices. Virtual particles do this constantly. They don't violate conservation on average or over long times. But they blur the line between allowed and forbidden. The second law can be violated in small systems. If you watch a single molecule, it might move against a thermal gradient due to random kicks from surrounding molecules. Experiments with colloidal particles and optical traps have observed entropy decreasing in microscopic systems over short times. These violations don't threaten thermodynamics because they even out statistically. Over many trials, entropy increases, but they show the second law is statistical, not ironclad at small scales. Maxwell's demon, a thought experiment proposed by James Clerk Maxwell in 1867, imagines a tiny being that sorts fast and slow molecules, creating a temperature difference without doing work, apparently violating the second law. Modern analysis shows that the demon must store information about the molecules. Erasing that information generates entropy, restoring the second law. Information and entropy are linked. Leo Szilard showed in 1929 that information has entropy. Claude Shannon formalized information entropy in 1948. The connection between thermodynamic entropy and information entropy is deep. Black hole entropy is related to information lost behind the event horizon. The black hole information paradox asks whether information is destroyed when it falls into a black hole. Hawking radiation seems thermal, carrying no information. But quantum mechanics says information can't be destroyed. Resolving this requires quantum gravity, a theory we don't fully have yet. Candidates include string theory, loop quantum gravity, and others. None are proven. Until we understand quantum gravity, the ultimate fate of information in black holes and in a heat-dead universe remains uncertain. That uncertainty means the rules as stated might not be the final word. The third law, no absolute zero, is absolute within known physics. But if new physics exists at ultra-low temperatures, perhaps Planck scale phenomena, the third law might have exceptions. Approaching absolute zero concentrates quantum effects. Bose-Einstein condensates form when bosons occupy the same quantum state. Atoms lose individual identity and behave as a single quantum entity. Temperatures below a microkelvin have been achieved. Researchers probe quantum behavior in these regimes. So far, nothing violates the third law, but experiments continue. Proton decay would show that baryon number isn't conserved. That changes the rules. Suddenly, matter is temporary. Atoms have expiration dates. The universe's long-term structure vanishes. The proton decay experiments continue at super Kamiokande, now upgraded to hyper Kamiokande, with 5 to 10 times better sensitivity. If proton decay is just beyond current limits, the upgrade might detect it. If the lifetime is 10 to the 36th power years or longer, we may never see it. But the possibility keeps physicists watching tanks of water deep underground, waiting for a proton to flash into gamma rays. Vacuum decay, if it happens, rewrites the rules instantly. Inside the bubble, different laws apply. The Higgs field's new value changes particle masses. Chemistry changes. Stars and planets dissolve. Life ends. But the bubble hasn't formed. The vacuum is stable enough, for now. As mentioned, the lifetime exceeds the age of the universe by an incomprehensible margin. We're safe, probably. The experiment developed an effective model capturing initial bubble creation and subsequent interactions, accurate under dissipation. Coherent scaling laws appeared in the driven many-body dynamics for more than 1,000 intrinsic qubit time units. This confirms theoretical predictions about bubble nucleation. It shows that quantum field theory processes can be emulated in atomic systems. The hot Big Bang in a cold gas, as Newcastle University's Professor Ian Moss called it. The January 11th, 2024 seminar discussed in the Tunneling in QFT series at CERN examined how false vacuum decay plays a role in the formation of matter and the origin of the universe. The processes that might have created the Big Bang from a quantum fluctuation in a false vacuum are the same processes that could, in principle, destroy our universe if the vacuum tunnels to a lower state. The difference is scale and probability. The early universe was tiny, dense, high energy. Quantum fluctuations were frequent. A tunneling event creating a true vacuum bubble that expanded into the Big Bang was unlikely, but not astronomically so. Today, the universe is vast, diffuse, low energy. Quantum fluctuations are rare per unit volume. A tunneling event nucleating vacuum decay is astronomically unlikely, not impossible, just improbable enough that we don't worry. Together, these rules create a universe that starts with a bang, burns bright for billions of years, cools gradually, and fades into heat death over timescales that dwarf comprehension. But within that vast stretch, complexity emerges. Stars form, planets coalesce, life arises, consciousness develops, civilizations build, all because the rules permit it. The rules don't mandate life, they just allow it. We're a side effect of thermodynamics, an eddy in the flow toward equilibrium. But eddies can be interesting. And until heat death arrives in 10 to the 106th power years, or vacuum decay erases us, or protons decay, or dark energy rips space apart, the rules keep the show running, energy transforms, entropy climbs, motion persists, the universe continues. In 2025, a February 27th Physical Review D paper by Human Davudiassel and Peter Denton examined terrestrial and astrophysical constraints on proton stability. They found that Earth's solid iron core, which has been solid for 1 to 4 billion years, would have melted if the local proton lifetime were shorter than 2 times 10 to the 18th power years. The core temperature is about 6,200 Kelvin. If protons decayed producing heat at a rate 4 times the current inner core's 13 terawatts of radiative output, the core would remain molten. It's not. That sets a lower bound. But 2 times 10 to the 18th power years is vastly shorter than laboratory limits of 10 to the 34th power years. The discrepancy suggests proton stability varies with location or time. The authors propose a long-range force whose strength changes as the Sun orbits the Milky Way center every 230 million years. During different orbital phases, the force's intensity shifts, altering proton decay rates, This remains hypothetical. No such force has been detected, but it illustrates how much we still don't know. The rules we've described, conservation laws, thermodynamics, quantum mechanics, are tested in laboratories and near Earth. Do they hold across the galaxy, across the universe, across all time? We assume yes, but we can't test everywhere and every when. If the proton lifetime changes with position or epoch, then the rules aren't universal, they're local. That shakes the foundation of physics. Fundamental constants aren't supposed to vary. The speed of light, Newton's gravitational constant, Planck's constant, Boltzmann's constant, these are constants. If they change, they're not constants. They're fields or variables. That would require new physics, possibly a fifth force, possibly extra dimensions, possibly modification to general relativity. The exploration continues. The rules as we know them prevent the universe from freezing over today. Whether they'll hold forever or whether something unexpected breaks them, we'll only learn by watching, measuring, and surviving long enough to find out. The universe is under no obligation to follow rules we invented. But so far it seems to. Energy stays, entropy climbs, zero stays out of reach, and the cosmos keeps evolving, one quantum fluctuation at a time, toward an end we can calculate but not escape.